How does an LSR, a label switching router, choose the best path when it has multiple people advertising labels to it? Well, that, my friend, is the subject of this video, and choosing the best label switch path. Let's jump in. Here are the opt-out questions for this video, so take a moment, read through these questions, and if you're already comfortable and understand the content behind the questions, hey, jump to the next video. Otherwise, stick with me right here as we cover these topics. Let's begin. I'd like to ask you a question about Bob. Let's go ahead and put Bob right here, and we'll give him a name. There we go. So let's say Bob is a fully functional, fully capable adult, and let's say he's happy as well. Now here's my question. Regarding Bob, who is responsible for Bob's life? And I think a lot of us are going to agree that for most everything, Bob is really responsible for himself. And that goes the same for you and I respectively. We're responsible for ourselves. So as we progress through this life, we have opportunities to learn things. Maybe we're given a book or shown a video, and maybe we read that book or watch that video or take advantage of those opportunities as they come up, or possibly not. And those choices are really up to us what we do with those opportunities. Now you might ask, what does that got to do with these routers over here? Well, with these routers, they are also given information. For example, regarding IPv4 routing, we're going to have a control plane. And for IPv4, we maybe use something like OSPF. That trains these routers, gives them information on how to reach various networks. But at the end of the day, after this router has been given all that information, it's really up to this router to decide on its own, based on all the information it has, which way it's going to forward a packet based on everything that it knows. Well, with labels, we also have a control plane. And with labels, we're using label distribution protocol as one, not the only, but one of our methods for distributing labels. And so at the end of the day, R2 is going to be advertised labels from R1 and labels from R3 regarding different networks. And R2 is responsible for making a choice based on all that information of how he's going to forward traffic. Is he going to forward towards R1 or is he going to forward to R3? So together, I think we should review the decisions that a router is going to make based on the information that is given. Let's start off with a routing protocol with IPv4. And let's take the network 5.5.5.5.5. And for our example, we'll call that a 32-bit network. So if R2 learns about 5.5.5.5 via OSPF, and this is all one OSPF area, R2 doesn't have a whole bunch of choices. It pretty much knows that the next hop, this direction, is going to be the best path because it has the link state advertisements directly from R5 regarding that network, and it doesn't have a whole bunch of choices. Not only is this path the best cost, it's the only path available from an IPv4 perspective. However, if we threw in RIP, for example, I don't know why we would, but let's say we threw in RIP version 2 at the same time, and router 2 is now looking at OSPF learned routes and RIP learned routes. If both of those protocols are advertising the 5555/32 network, then R2 is going to go with administrative distance, choosing the lower of the two. So OSPF is at 110, RIP is at 120, and it would choose OSPF. However, if OSPF was advertising a route of 5550/24 and RIP was advertising a route of 5555/32, because the 32-bit route would be a longest match, in that case, the router would choose for 5555, it would use the RIP learned route. So it's the longest match first for IP version 4, and then if we have equal length routes coming in from two different routing protocols, we're going to base it on the lowest administrative distance between those two. And if we have multiple routes from the same exact routing protocol, we might get into a situation where we'll do load balancing across multiple paths. So that's a sampling of considerations that R2 might go through when choosing a best route to reach some IPv4 network. And let's say that to reach 5.5.5.5, R2 determined that R3 is the next hop. So the next hop would be 10.23.0.3. And R3 determines that the next hop is going to be R4, 10.34.0.4. And R5 is directly connected, so that's the end of the road. And from R1's perspective, the next hop would be R2's address of 10.14.0.2. So all these routers, based on the IGP, the Interior Gateway Protocol, they know, in this case OSPF, they know exactly what the next IPv4 hop is to get to a given destination network. And with Cisco routers, they only put the best route in the routing table. For example, if R2 had two routes, one was good and one was not good, it only shows you the good one in the routing table. The routing table is like the winners list of those routes that are actually going to be used. The ones that are like second place or standby, they don't show up in the routing table. Now with LDP, let's go ahead and sit in R2's shoes just for a moment. R2 is going to be receiving advertisements from R3 and also from R5. And that's because label switch routers running LDP are going to advertise their mappings, their local mappings to the prefixes they're mapped to all of their neighbors, upstream and downstream. So with a reference to network 5555, I'd like you to think of it like a pool of water, like a lake, if you will. So we have a lake of 5.5.5.5. And I'd like you to imagine as a lake with no outlets. It's not letting any water out, but we have some streams that are putting water into this lake. Now my question is regarding this stream, if we're going this direction, would that be upstream or downstream? That'd be downstream. And regarding anything that was going the other direction, I don't know if we had like fish that were jumping up the water, that would be upstream. So from an LDP discussion perspective, when we talk about downstream, it's towards the actual target network, and upstream is moving away from the reference network. So from R3's perspective, it would know from its IGP about network 5555. It would generate a local label for that. It would advertise that label downstream towards R4 and upstream towards R2. So in this example, R3 is advertising a local label mapping for 5555 over to R2, and R1 is also advertising its local label mapping for 555 over to R2. And what R2 is going to do is going to use something called liberal label retention, meaning it's going to remember both of the advertisements, one from R3 and one from R1 regarding the 555 network. Now it does that in case there's some type of change in the network and it loses its primary path. It can very quickly cut over to the alternate path. Because of liberal label retention, it's going to remember, hey, R1 advertised a label for 5555 in case R3 goes away. Now the reality is if R3 went away, R5 would lose the 555 network because it's way over here and there's only one path, and that would cause R1 to stop advertising a label. So in a network where we had multiple paths and fault tolerance built into the infrastructure, the liberal label retention helps for a quicker cutover to an alternate path if we need it. But here's the real problem for R2. It's receiving two advertised labels, both for 5555. And the question is, which one should it use? Should it use the label that R1 is advertising and forward packets this way? Or should it use the label that R3 is advertising and move a packet destined for 5555 that way with the appropriate label that R3 is advertising? Now, looking at this diagram, we can say, oh, Keith, this is obvious. We'd want to go this way because it's the only way to get to 5555. But routers don't really have great eyesight. So how does the router figure it out? And my friend, this is the process that the router goes through to figure out which of the advertised LDP neighbors labels it should use as the best path to get to the final destination. And here's the step-by-step process. So first, regarding network X. In our case, we're going to say network X is 5.5.5.5. The first question we ask is, who are my LDP neighbors? If you only have a single LDP neighbor and they're advertising a label for 5555, you don't have much of a decision to make. You have one choice as far as LDP goes, and MPLS, you're going to use that neighbor. Now, presuming we have two or more neighbors and they are both advertising labels for network X, in this example for 5555, the next question we ask ourselves is, who owns the next hop IPv4 address for network X? So this one statement right here basically says, let's refer to the IPv4 routing table and see what the next IPv4 next hop address is. Now on R2, if the routing table says, oh, the next hop is 10.23.0.3, which it is, I'm going to write that out right here, 10.23.0.3. So based on what we learned via OSPF or IGP, or it very well could have been a static route that said this is your next hop for 5555, it really doesn't matter how or why R2 believes that's the next hop, but if it does, the last step is to choose the neighbor, the LDP neighbor between R1 and R3 who owns this IP address, 10.23.0.3. Because in the LDP session, what we're going to share with the neighbor is not only the fact that, hey, we want to be a neighbor with you with LDP and here's all my mappings, we're also going to share with our neighbor all of our local IP addresses. So loopback addresses, physical interface addresses, and that's the reason that R2 can say, okay, the next hop is 10.23.0.3. Who owns that next IP address? Is it R3? Did he tell me he has that IP address via LDP? or is it R1? So based on which neighbor owns the next IPv4 hop, that is the neighbor that we're going to use for our MPLS forwarding table on the router. So let's walk through that entire process on R2 regarding 5.5.5.5, that 32-bit network. The first thing we're going to do is let's ask R2, who's your neighbor? Won't you please, won't you be my LDP neighbor? And he's got two neighbors, R3 and R1, exactly as we would expect. So we've got two LDP sessions going on, one between R1 and R2, and one between R2 and R3. And if you'll notice, part of the information that R2 knows about each of its peers, it says regarding 1111, I know he has these local addresses of 10.14.01 and 1.1.1.1. Those were part of the LDP communications in the session between the two of them. It also knows that this neighbor of R3 has these three IP addresses directly associated with that router. So from R3's perspective, here's R3's loopback. The 10.23.03 would be this interface, and the 10.34.03 would be this interface. So we've got two neighbors. Let's take a look at all of the LDP bindings regarding 5555, our local bindings and any remote bindings that we've learned either from R1 or R3. So our local label is 203, that's the one we chose to assign to 5555. And we've learned the label of 102 from R1 and label 303 from R3. Now the question is, which one of these should we use if we ever need to forward a packet to 5555? Should we label it up with a 102 and send it to R1, or should we label it up with a 303 and send it to R3? And the reason that both of these labels are showing up, even though one's really good for forwarding and one's not, is because of the liberal label retention mode that this router is using. So regarding 5555, our next question is, okay, from an IPv4 perspective, what is the next hop we would use if we were going to forward an IPv4 packet to that destination? So we can find that out just by looking at the routing table with the show IP route, and we'll just use an include statement to say, just show us stuff that's regarding 5.5.5.5 in the output. So from R2's perspective, he says, sure enough, to get to 5555, I learned it via OSPF. There's the administrative distance for OSPF. There's the cost. And the next hop is going to be 10.23.0.3 to get there. And the egress interface I'm going to use is gig 20. So the key element right here is that the next hop, the next IPv4 hop, is 10.23.0.3. And if we look up at the neighbor statement, check it out. The peer at 3333, that router ID, owns that next hop of 10.23.0.3. And it's for that reason that R2 is going to say, you know what, to build my MPLS forwarding table, I'm going to choose 3.3.3.3 and whatever label that's been advertised by 3.3.3.3, which in this case is label 303, for my forwarding. And you and I can verify that just by asking it, please show us the MPLS forwarding table for 5.5.5.5. And it says, sure enough, I'm going to go ahead and use label 303. The outgoing interface is going to be gig 2/0, and that packet is going to the device at 10.23.0.3, which is R3. So we're going to label switch in the direction of R3. And we're going to put label 303 on that packet in the MPLS header before we send it. So for example, if R1 was actually pinging R5, R1 would impose the label of 203 for us. We would swap that out with 303 and simply label switch it on its way. And this label switch path is unidirectional. You could have label switch paths that go over one set of routers one direction and yet a different set of routers in the other direction. And by default, this LSP is driven based on your IGP. Whatever IPv4 is using as its best path, your label switch paths are going to follow that same exact path by default. Now, there are times when we might want to modify that or manipulate that with something called MPLS traffic engineering. That's when we force an LSP across a path other than what the traditional IPv4 forwarding path would be. And we'll get more into that in the intermediate and advanced MPLS courses. Now, what we could do, and I think we should do because this is a lab environment, is let's go ahead and mess with R2's brain. What if we told R2 that from an IPv4 routing perspective, the best way to get to 5555 wasn't this way with the next hop of 10.23.0.3, which it currently believes due to OSPF, but instead, what if we did a static route that has a lower administrative distance that says, instead of going right, go down to R1. If we change the routing table on R2, either through static routes or by manipulating the IGP, that will also affect our LSP. So for a demonstration like this, if we do tell R2 that to get to 5.5.5.5, we'd want to go this way, we're really breaking our network. But as an exercise in testing and verifying that that's really how it works, I think we got to go ahead and do it. So on R2, we'll go into configuration mode and we'll say, hey, here's a static route to get to 5555/32. Your next hop is 10.14.0.1, which is R1. And we'll just do a show IP route just to validate that what we thought we put in for a static route actually took. So at the winners table, which is often referred to as the routing table, the best route now is our static route to get to 5555. Our next hop is 10.14.0.1. Now to verify that, check this out. We'll go ahead and do a show MPLS forwarding table again for 5.5.5.5. I just added that do command in front because I am in configuration mode. And take a look at the new outgoing label. It used to say, hey, we're going to use label 303 and send it out gig 20, but now our label switching path says we're going to use label 102 and we're going to send it out gig 1/0. Now the reality is, right now, if we had a packet that R1 sourced that was going to 5.5.5.5, it would be MPLS switched. So we would impose label 203, R2 would get it, swap that label, it would put on 102, send it right back, and we would have a loop right here between R1 and R2. But it wouldn't go on forever because we have the TTL in the MPLS header that would decrement every time it goes through one of the routers. And when that TTL expires, we're going to kill that packet. So we could have some fun with that. Let's get out of configuration mode and do a ping of 5555 with a repeat count of 1. Now, that's not coming back. However, that packet does have the potential for looping through the network between R1 and R2. Now, because R1 sourced that packet, it's really hard to tell whether or not the TTL really was set to 255 or not. But have no fear. We could put Wireshark on that link and simply take a look and see what's really happening. If there is a loop, we can go ahead and see all of that traffic going through. Let me also just go ahead and do a show MPLS forwarding table for 5555 and look at this. Number of bytes label switched, 38,000 bytes. And that was just from that one ping. So it was so fun. Let's do it again. If we just do another ping again. In fact, let's also capture it with Wireshark. So in GNS3, I'm going to right click on that link between R1 and R2 and say start capturing to let that run while it goes. And we'll go ahead and do a repeat count of 1 for our ping. So sure enough, we just have a boatload of traffic. So I'm going to stop the capture. That was a lot of packets. And if we just grab some near the middle, here we have all the ping requests that are just looping through the network. And then we have a whole bunch of time to live exceeded messages coming back as a result of the TTL going down to 0. So for example, this one packet right there, we've got a TTL of 4. If we look at that same spot on the next packet, we have a TTL of 3, a TTL of 2, a TTL of 1. And that was all from one single ping. So let's go ahead and fix that problem on R2 so we don't have that loop. So we're going to go back into configuration mode and bring up the static route and simply say no. And now that the static route is gone, the LSP is going to be back in place pointing to R3 instead of R1. And we've solved in one fell swoop our IPv4 routing problem and our LSP problem. So we'll go ahead and just do a quick ping again, and that should work no problem without the loop. So my friend, the key to success in this is to practice everything that we've done together. And we're still using the topology that we implemented in the video called Implementing MPLS. Now, part of the steps we did in this video was to put that static route in to change the IPv4 routing, which changes the LSP. And I'd like you to do that so you can see those effects. So a little tip, when you put in that static route to manipulate the path that IPv4 would take, and you mess up the LSP at the same time, do that for testing and verify it, but make sure you do not save the configuration with that static route in place. Because as you and I continue to build our network, we want to make sure we have a good foundation to continue working on, which implies good IPv4 routing and correct LSPs that actually work. The other thing I'd love for you to do is go back to the opt-out questions at the beginning of this video and to review those to make sure that you're now comfortable with those questions. And that'll help confirm your understanding of the content. I have had a blast and I'm so glad that you joined me for this video. I hope this has been informative for you, and I'd like to thank you for viewing.